We're at episode 5 of our arcade dev project. This time we're going to get a tilemap render engine going on the breadboard. I'll be stepping through how all that works right now. Let's get going! The Tank Battalion game that we're recreating uses primarily tilemap graphics. There's a great blog called the Retro Game Deconstruction Zone, link in the description. I can't think of a better way to explain tilemap graphics than that site, so if you're interested, please take a visit and a read of that page. You can see tilemap graphics are a way of storing data, let's say 8x8 pixel squares of data in a read-only memory. The beauty of the system is that the CPU can then point to the address of that data, let's say a letter or number with only a single byte address, and then locate that in the ROM. It is super quick since you only need to move around that single byte of data. It's been used extensively to store background data, the mazes in Pac-Man, and can also have color info there as well. We can see exactly how that works coming up. The image on the screen is our circuit outputting a single small tank character over and over again. To see how it's done, we need to understand how the circuit works. The tilemap render circuit is made up of 5 main IC components and a timing component. I'll do a quick run through of the chips that we'll take a deeper look at later on and exactly how it works. We'll start with the 2L IC, the 74LS273. That is an 8-line D flip-flop. It's the same as the D flip-flops we've previously seen, but in this case there are 8 inputs and 8 outputs. As we'll see, it's used as a register to store a byte of data on the display bus. Next up, the data splits into 2 directions. In one direction, the data bus goes to the 2K Character EPROM. This is the chip that contains all the character data for the tilemap. That chip outputs a byte of data with information about a single 8 pixels to the chip 2J. This chip is the linear pixel renderer and changes that 8-bit wide byte into a steady signal of 1s and 0s to allow us to display something on the screen or not. The 3 chips below create the correct timing so that these render chips are always triggering in time to show what we want to correctly on the screen. The second part of data from the 2L chip goes directly to the 3J chip. There is another D flip-flop chip, this time with only 6 inputs and 6 outputs. We'll see how the data is being manipulated soon, but eventually the 3L color PROM chip, which is shown here on the right, takes in the data from the 3J chip and the pixel renderer and comes up with a color pixel for the screen. This is then output onto the color pins of red, green or blue and then goes to the TV screen. It's a really elegant design and is one of the simplest to understand, although I think we'll need to do a walkthrough to understand it a bit more. Great to think how it's doing all that with such few components. So, here's the same circuit on the breadboard. In order to create a useful changeable data input device, I've included an 8-switch dip switch at the first part of the circuit. That red dip switch allows me to input any byte of data that I want, and so select a character to show on the screen. Next up, we have the 74LS273 chip as the input register to hold the data. It's not really needed here, since the dip switch is already holding the data pretty firm. Next, we have the Character EPROM. It's a bigger chip, as we'll see coming up. Then we have the 74LS166 parallel shift register to output the pixel stream. Finally, we have the 74LS174 flip-flop again, and then the 7052 or 2125 color PROM chip. That's the one that defines which color to output onto the screen. As per the last episode, we have our output hooked up to the socket connected to the PVM display. In terms of connections, we have the dip switch, each switch connected to ground on the left side, and on the right side all connected to 5 volts through a 2.2k resistor. It doesn't matter too much, around 1k is fine. Then on the right hand side, all dips are connected through the grey wires to the 74LS273D inputs. For any chips that show RP on the schematic, these pins are tied to a pull-up resistor that's typically a 1k resistor between the pin and the 5 volt rail. For the 273, the Q outputs are connected to the 2716 EEPROM chip. The address lines for A10 to A3 only. The 273 clock is connected to the H4 output from the LS161 we've seen in the previous episodes. The 2716 EEPROM has the remaining address lines of A2, A1 and A0 connected to the V4, V2 and V1 lines from the LS161. We'll see why a bit later. There is no clock on actual ROM or SRAM in these designs, but we do have 2 chip enable pins. Those are both active low, meaning the chip is enabled when it's low. So I've tied these pins to ground. It's a bit different to the schematic, but it's fine for now. The output data pins of the 2716 EEPROM chip are connected to the 74LS166 chip and are the inputs there. The loading pin is driven by the timing circuit shown below here. The clock circuit for shifting right is the 6 MHz signal from the previous timing circuit that we built. A couple of the pins are tied low on the 166 and the serial output pin is connected to the color PROM chip. The D flip-flop chip 174 is connected to the 2716 EEPROM chip on the board to shorten the length of the wires, but only connect 6 of the lines, and the chip is clocked using the same timing circuitry that we had on the 166 chip. Then the color PROM chip is connected to the 174 flip-flop 6 outputs and also has 2 other important inputs. The A1 input is actually from the sprite circuitry. We're not doing that part just yet, so I've just tied that to ground, giving a 0 input for this time. The A0 input is the output from the 166 shift register. This is what's going to show us a pixel or not on our tile graphics. Finally, the output of the color PROM is attached to the PVM as shown for the red, green and blue. There is an additional pin that slightly increases the brightness of the pixel, although it seems to be minimal. The color PROM. This chip is a bipolar programmable read-only memory chip. I've put a datasheet on the GitHub for reference. It's a small 16-pin chip of 256 bits by 4 bits that is used for color palettes in many of the early arcade games. The beauty of this setup is that the color palette could be interchanged by just using different PROM chips. I think that these chips are quite fast in their operation since they need to be working at 6 MHz to get the color info on the pins. Apparently, the bipolar PROM is programmed by effectively blowing tiny fuses inside the chip. Obviously, once it's programmed, it can't be reprogrammed. In addition, these days, these chips are very hard to come by. They're also very hard to program. In fact, you need a special programmer which isn't really economical to buy for the small use you'd get out of it these days. I bought this chip from a US supplier, and there's a chap in Canada that will program the chip for you for a good price. The service was quick and excellent. If you're interested, drop me a line in the comments. Later in this video, I show we can use a normal EEPROM for the color PROM. It's not perfect, but it behaves just as good for what we're trying to do. You can see the chip has 7 input address lines to address those 256 addresses and has 4 output bits. Those create the red, green and blue signals. We'll see just how later. There are 2 chip enable pins that enable when set low. You may remember from the last video that we connect the V blank to these chips, and we only want the chip to display something when we don't have the V blank. You can see here the contents of the color PROM. I've used a hex editor called HXD to open this file, and I found the Tank Battalion ROMs online for use in MAME. You can see it's a small ROM file with 256 addresses, and for each address a byte of data. In fact, it's only a nibble of data, being half the byte. It just happens to show a byte here in the software. The contents of the nibble make up the color as shown in the graphic. For example, the number 2 is the second bit, which corresponds to the red connection on the monitor. As we saw in the last episode, you can make quite a few colors if you add the 3 colors together. You can see here how the PROM chip connects up to the display, so the 3 or in fact 4 pins output the color. The 2716 EEPROM chip is an erasable, programmable, read-only memory chip. You can see it has a little window in order to erase the data by shining UV light onto the actual cells inside the glass. This particular version, the 2716, is a 2 kilobit by 8-bit size, meaning it can store 2 kilobytes. I've added a reference datasheet to the GitHub for this chip. The whole arcade board uses 5 of these chips, 4 for the game ROMs and 1 for the character ROM that we're playing with in this episode. I'm showing here the device to erase an EEPROM. It's simply just a plastic device that has a drawer to place the EEPROM chip, a switch to turn on the UV bulb, and a timer to auto switch off the bulb. Typically 10 to 15 minutes of UV out of these and it will be erased. Note that they are raised to the FF hex state, or fully on, not the 0 state. This is the EEPROM programmer that I use, the GQ4X4. It's a good programmer, a little better than the cheaper Chinese model that most people use. The reason why I needed this one is those newer Chinese programmers can't handle 25 volts that is needed to program older EEPROM chips that you might find in some arcade boards. You can work around that, but it's a useful programmer. The pinout of the 2716 is 11 address pins, A10 to A0, and 8 data pins, Q7 to Q0. There are a couple of enable pins that need to be kept low to operate the chip, and then there is the power pin on pin 21 that is used when programming the chip. We can ignore this pin when just using it as a ROM chip. Here is what the hex data looks like for the character ROM. We'll see how it's working a little later, but it's providing a byte value for each 8-pixel line of a character. The parallel shift register 74LS166 is a really interesting chip. It takes a byte of data, 8 bits, and then splits the data out in a serial output, 1 bit after the other on every clock cycle. It therefore has 8 parallel inputs, a serial output, and a loading pin on pin 15 to load the data in. It also has serial input and parallel output if you want to use it the opposite way round. The logic table shows how the load takes in the data, and then on the positive edge of the clock cycle, you start shifting through the data you just loaded. In this example here, we're loading the hex value AD, which is equal to 10101101. You can see here that when the load pin goes low, it loads the AD, and then on the next positive clock cycles, it outputs the 1010 and then 1101. Imagine if that is then an input to the color PROM chip. It would be the line pattern of a character in the ROM. The chip doesn't carry on outputting if it's worked through its bits and doesn't have a new set loaded. The other supporting ICs, one to note, is the 74LS139. This is a 4-line decoder demultiplexer. It's a fancy name, and in this instance it's just taking 2 bits of data and deciding which of the 4 outputs to select. As you can imagine, with 2 bits of data we can create 4 possible combinations of 1s and 0s. This type of chip is often used for address decoding to select a certain bank of memory by the CPU. We'll see more about that in later videos. For now, all this chip is doing is creating a loading trigger for that LS166 that we talked about. I'll show you the logic traces of that chip later to understand what it's looking like. The 74LS174 is just a hex flip-flop, meaning there are 6 flip-flops in the chip. We're using it as a storage register for our 6 bits of data. The 74LS273 is the same thing but an octal type, meaning there are 8 of them in this chip. Again, we're using this chip as a storage register for the 8 bits of data input into the video circuitry. Other than that, it's behaving just how we've previously seen the D flip-flops behave. To show how the Tilemap renderer engine works, we're going to do a worked example. We're going to use the tank character as our example. I've downloaded the character map from MAME. We'll take a look at the usefulness of MAME for programming, hacking and debugging in another video, but from this graphic we can see that the tank character we're interested in is triggered by inputting the byte CE in hex. This is equal to the bits 1100, 1110 in binary, from the highest bit to the lowest bit. Now, one thing to bear in mind with this is that we actually have a vertical game with Tank Battalion. That means the entire display is rotated 90 degrees when we play it. However, it's not rotated to display it. The tank we're plotting though is actually on its side, like shown. So the dip switches are set to equal those binary inputs. This is then used as an input for the chip 2L. The chip clocks at 4H speed, which I think we said happens to be about 1 MHz. The output from that chip goes 2 ways. First, let's look at how it goes to the EEPROM character chip at 2K. The 8-bit address is added to with another 3 bits, using the 4V, 2V and 1V. This actually is triggered on the next vertical lines of the screen. If we add the 3 bits, we now have an 11-bit wide address. This therefore becomes 110, 0111, 0000. In hex, this is the number 670. Now if we go to the location of 670 in our ROM data, you can see we have the byte 00. This 00 is output to the shift register in an 8-bit byte. Since this is a 0 input, we can imagine we have a 0 output from the serial pixel renderer. Back to the other path from 2L, and we take only the highest 6 bits from the 2L output and use it as an input to the chip 3J. This is essentially passed through with the same 6 bits clocked on the 4C pin 11 clock. Finally, the color PROM chip 3L takes in the 6-bit output from 3J and puts it in the 6 highest bit places. It adds another 2 bits. The A1 bit is from the sprite renderer, which we haven't implemented yet, and so stays 0. The A0 is the output from the pixel renderer from the Tilemap. We know on this first go around it's only 0. The entire output is enabled only if there isn't a VBlank happening. So the final address is 11001100. This is equal to the hex address of CC. Of course, that is a value of 0, meaning there's no color output. That makes sense since we didn't have any line being output from our pixel render chip. Okay, well that was limited in usefulness for understanding, so let's go back and see what happens on the next vertical line. So the next vertical line has the same input into 2L, but this time for the 2K, the 1V is high, making the input to the 2K chip now 11001110001. This is equivalent to the hex number 671 rather than 670. At location 671, we have the hex byte result of 1F, so 1F becomes the input into chip 2J. This time we have data to pass. It turns out that the 1F equals the string of 00011111. When we feed this input into the color PROM chip 3L, we now have 2 addresses. 11001100, which we saw with CC, but now 11001101. This is CD in the PROM chip. The output to this is 0C, or in fact only C, since it's a 4-bit nibble. If we look at what C means, it's high for bits 4 and 3, which is the green and blue color. We know from the last episode that green plus blue equals cyan. Therefore, we get the cyan color for our tank whenever we have the pixels for the tank. The rest is just the other V inputs to 2K working through the next parts of the character ROM for each of the 8 vertical lines. The 3 vertical timer input bits make a value of 0 to 7 to add on to the reference location in the ROM. So hopefully it's now clear how the Tilemap ROM is creating the picture. It's a pretty elegant solution that only needs 1 byte to display 8x8 pixel squares on the screen. Here we've got the logic analyzer hooked up to the main timing trigger. The main outputs are the 256H, which you'll remember is the H-blank signal. The final output to the 4C chip, pin 11, is a negative pulse for every new character load period. It's the trigger for loading the next character block into the parallel shift register and loading the next color ROM info. One point to note is I'm pretty sure the schematic is wrong here, because we'll see in later videos that the timing is not quite right if it's hooked up this way. It's a simple fix though. The logic analyzer is on the 8-bit shift register. We have the 8-bit inputs A to H, with the load trigger, the pink trace, the 6 MHz clock, and then the final output is green, the QH. Interesting to see each input has a regular blip on there. This must be something to do with the loading from the ROM chip. It doesn't affect anything, since those blips are there during the H-blank portion of the triggering. You can see that the green output serial bits are between the pink load portions, as we'd expect. On this final graphic, we can see the output of the serial pixel renderer. I've chosen 3 of the outputs, with the associated part highlighted in red on the right. You can see the first one has no pixels, so it's all zeros. Then the next one has a set of continuous ones, so is shown in the middle plot. The third plot is one part of the tank with the gun, so has 3 ones in the line. So hopefully it's easy to understand how the pixel renderer is plotting the info. Earlier in the video, I suggested that it's quite difficult to get the small color PROM chips programmed due to the old technology they use. I wanted to see if we can replace that PROM chip with a more typical EEPROM, like the 2716 we've been using for the character ROM. To do that, I burned the color PROM hex data to the lower part of the 2716 ROM and left the rest blank. You can see here I've removed the other color PROM and connected jumper wires to the 2716 test color PROM. When we power on the breadboard, we do get a successful image. There are a few small artifacts at the leftmost edge of the screen. I suspect the typical color PROMs may work a little faster, and that's one of the reasons why they're used. For now though, to prove our system, I think this is a satisfactory solution. Right, well that's episode 5 wrapped up. It's getting interesting now. Next time we'll add a video memory to our Tilemap display to get a more interesting picture on the screen. See you next time.